This lecture begins Chapter 5, The Formation of Stars and Planets. This lecture will discuss parallax and the discovery of exoplanets. Parallax is the displacement or difference in the apparent position of an object viewed along two different lines of sight, and is measured by an angle or semi-angle of inclination between those two lines. Parallax is used in surveying to measure distances, and parallax gives us stereo vision. Astronomical parallax is the apparent shift in a star's position throughout the year. The background stars are stars so distant from Earth that no parallax can be seen. The closer a star is to Earth, the more it seems to shift its position back and forth with respect to the background stars, just as your thumb at arm's length appears to change position with respect to the distant wall. It was the lack of observation of parallax that led the Greeks to think that the Earth does not go around the sun. The first parallax observation was made in 1806 by Giuseppe Calandrelli on the star Vega. In 1838, Friedrich Bessel made the first successful parallax measurement ever for the star 61 Cygni. Bessel found that 61 Cygni had a parallax of 0.314 arcseconds, which, given the diameter of Earth's orbit, indicated the star is 10.3 light years away. 1 parsec is the distance at which one astronomical unit subtends an angle of 1 arcsecond. A parsec is equal to about 3.26 light years, which is 31 trillion kilometers, or about 19 trillion miles. Using your eyes and thumb, the parallactic angle for your thumb, that is the amount of shift of your thumb as you view alternatively your left and right eye, is 6.5 degrees. The largest stellar parallax is seen with Proxima Centauri, which has a parallax of 0.7687 arcseconds, which is 0.0002135 degrees. This is equivalent to an arm length of 6.3 miles. The Hipparcos Space Astrometry mission pinpointed the positions of more than 100,000 stars with high precision, and more than 1 million stars with lesser precision. For 118,000 selected stars, Hipparcos measured their parallax accurate to 0.001 second of arc, and another million stars to an accuracy of 0.01 second. Hipparcos measured stellar distances by the parallax method up to 1,600 light years away. Watch the accompanying video posted on Blackboard for more information about Hipparcos. The main goal of the Gaia mission is to make the largest, most precise three-dimensional map of our galaxy by surveying an unprecedented 1% of the star's population of 100 billion stars. Gaia will detect and very accurately measure the motion of each star. Gaia is in orbit around the Sun at the second Lagrange point, L2, at a distance of 1.5 million kilometers from Earth and in the anti-Sun direction, and co-rotates with the Earth in its one-year orbit around the Sun. Gaia was launched on December 19, 2013. The image shows the reach of Gaia. Gaia is capable of measuring accurate distances out to the galactic center, around 25,000 light years. This accompanying video shows the 2,057,050 stars from the TGAS sample, which was published as part of the first release of ESA's Gaia mission on 14 September 2016, with the addition of 24,320 bright stars from the Hipparcos catalog that are not included in Gaia's first data release. The stars are plotted in galactic coordinates and use a rectangular projection. In this, the plane of the Milky Way stands out as a horizontal band with greater density of stars. The video starts from the position of stars as measured by Gaia between 2014 and 2015 and shows how these positions are expected to evolve in the future, based on the proper motions from TGAS. The frames in this video are separated by 750 years, and the overall sequence covers 5 million years. This video is posted on Blackboard for you to watch. This figure shows the expected motion of stars. There are 3 components to the motions. Top panel, the parallactic ellipse, caused by the motion of the Earth around the Sun. The size of the ellipse decreases linearly as distance increases. The second panel shows the star's proper motion, caused by its orbit in the Milky Way galaxy. The third panel wobbles in the motion of a star caused by the gravitational pull on the star by planets. The fourth panel, all the effects combined, illustrating the motion which Gaia will measure. Extrasolar planet is the term given to planets that orbit stars other than our Sun. We expect the laws of physics found around the Sun to be the same around other stars in the universe. The physical processes that lead to the solar system should be commonplace, so understanding exoplanets helps us understand our own solar system. The image is that of Beta Pictoris, which shows a young star with a disk of material and planets. The question is, how do we detect extrasolar planets? To understand exoplanets, we need a definition of what a planet is. These are the International Astronomical Union, the IAU, definitions of planet and dwarf planet. A planet is a celestial body that is in orbit around the Sun, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium, or nearly round shape, and has cleared the neighborhood around its orbit. A dwarf planet is a celestial body that is in orbit around the Sun, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a nearly hydrostatic equilibrium, or nearly round shape, has not cleared the neighborhood around its orbit, and is not a satellite of another object. All other objects except satellites orbiting the Sun shall be referred to as collectively as small solar system bodies. The Doppler effect is a change in frequency due to the motion of the source. This effect is heard as the changing pitch of an ambulance siren as it approaches you and as it passed by you. Several examples of the Doppler effect are given in the videos posted on Blackboard. Light also exhibits the Doppler effect. If the source of light is receding from you, the wavelength you detect is longer than that emitted by the source. The light is shifted toward the red end of the visible spectrum. This effect is called the redshift. The light you detect from a source moving toward you is blue shifted to shorter wavelengths. Radial velocity is the motion of an object directly toward or away from Earth. An object can be approaching Earth and the light would be blue shifted. An object can be receding away from Earth and it is redshifted. We use this change in wavelength to measure the motion of distant objects. Light from moving objects will appear to have different wavelengths depending on the relative motion of the source and the observer. Z is called the redshift. For motion like this, the first planets around other stars were detected. The methods of detection of exoplanets include the direct detection method of imaging and the indirect detection methods of radio velocity tracking, astrometry, pulsar timing, transits, and gravitational microlensing. The hardest way to detect an exoplanet is to try to image it directly. This is because of the extreme contrast between the light emitted by the parent star and by the companion planet. To expose the planet, the starlight must be dimmed or masked in some way as so to enable observers to see into the shadow. The figure shows one of the first images of an exoplanet, the red spot obtained. The planet orbits a brown dwarf, a blue spot in the middle. The The three known planets of the star HR 8799 as imaged by the Hale telescope. The light from the central star was blanked out by something known as a vector vortex coronagraph. It just has an opaque disk as the position of the star, blocking all of its light. This is another image of Beta Pictoris showing the debris disk and Beta Pictoris b, the orbiting planet. An indirect way to detect planets is by the radial velocity tracking. As the star moves in the small orbit resulting from the pull of the exoplanet, it will move towards the Earth and then away as it completes an orbit. The velocity of the star along the line of sight of an observer on Earth is its radial velocity as determined by the Doppler effect. Changes in its radial velocity of the star causes the lines in the star spectrum to shift towards a redder wavelength when the star is moving away from us and towards bluer wavelength when the planet is approaching us. The first exoplanet was detected on 6 October 1995 and was named 51 Pegasi b by the method of radial velocity tracking. You will follow this data when you do your lab activity. This diagram shows the effect of the star pulled slightly by an orbiting planet. The spectral lines shift back and forth. This is the Doppler effect. The amount of shift and the rate of change of the shift lets us know about the orbiting object. Astrometry is the branch of astronomy that involves precise measurements of the positions and movements of stars and other celestial bodies. The information obtained by astrometric measurements provides information on the kinematics and physical origin of the solar system and our galaxy, the Milky Way. The astrometry method is similar to radial velocity tracking and is used to detect exoplanets by measuring the small regular perturbation in the position of the star due to its unseen companion. The star moves in tiny circular orbit. A wobble is seen in the sky with a radius that depends on the mass of the planet and its distance from the star, but not on the inclination. The astrometry method is sensitive to planets on orbits greater than a year. This shows the motion of a star, the top looking down on the orbit and the bottom looking sideways. In both, the position of the star changes slightly, revealing the presence of a planet. We will explore pulsars in a later lecture, but pulsars are stars that emit regular pulses of light and radio signals. The presence of a planet orbiting a star affects the timing of the regular signals emitted by the star itself. This phenomena can be used to detect planets around a pulsar. Pulsars emit radio waves regularly as they rotate, creating a periodic pulse beam. Like a lighthouse, if an orbiting planet perturbs the motion of the star, then the timing of the beam is also affected. And this is how some of the first exoplanets were detected. When a planet passes between the Earth and its host star, this is known as a transit. The planet blocks some of the starlight during the transit and creates a periodic dip in the brightness of the star. This effect can be measured using photometry, which measures the amount of light coming from celestial objects. The figure shows brightness variations of two stars with transiting exoplanets. Notice the decrease in light as the planets partially block the parent star. In gravitational microlensing, the gravitational pull of a large object will bend the light from a distant object and amplify it, acting like a magnifying glass. When light from a background object travels toward Earth, its path is bent or warped as it passes any large foreground object that is aligned with the background light source. In 2003, the exoplanet OGLE 2003 BLG 235/MOA 2003 BLG-53 was the first planet discovered using this technique. The Kepler mission was specifically designed to survey our region of the Milky Way galaxy to discover hundreds of Earth-sized and smaller planets in or near the habitable zone and determine the fraction of the hundreds of billions of stars in our galaxy that might have such planets. The scientific objective of the Kepler mission is to explore the structure and diversity of planetary systems. This is achieved by surveying a large sample of stars to determine the percentage of terrestrial and larger planets that are in or near the habitable zone of a wide variety of stars, determine the distribution of sizes and shapes of the orbits of these planets, estimate how many planets there are in multiple star systems, determine the variety of orbit sizes and planet reflectivities, sizes, masses, and densities of short-period giant planets, identify additional members of each discovered planetary system using other techniques, and determine the properties of those stars that harbor planetary systems. This is a histogram of exoplanet discoveries as of November 26, 2017. Note the large spikes in later years due to the Kepler mission. These are some of the results of the Kepler mission. Many solar systems are not like ours. Many have hot Jupiters, Jupiter-sized planets close to the parent star, and many Earth-sized planets have been discovered by the Kepler spacecraft. Since Kepler launched in 2009, 21 planets less than twice the size of Earth have been discovered in their star's habitable zone, the region in a planetary system where liquid water might pool on the surface of an orbiting planet. These planets are plotted relative to the temperature of their star and with respect to the amount of energy received from their star in their orbit in Earth units. The sizes of an exoplanet indicates the sizes relative to one another. The images of Earth, Venus, and Mars are placed on this diagram for reference. The light and dark green shaded regions indicate the conservative and optimistic habitable zone. There are several videos in Blackboard about exoplanets for you to watch. In summary, parallax is a method of directly determining distances to objects by use of trigonometry. Thousands of exoplanets have now been discovered orbiting other stars.